Good day, everyone. In this video, I will have a discussion about one of the topics in hydraulics, which is the buoyancy. I'm Antonette Arpon, a third-year student from Bachelor of Science in Civil Engineering Section A at Eastern Visayas State University, Ormoc City Campus. Now that I have introduced myself, let's now proceed to the discussion. Let's say you have a heavy object in your hand, and then you hold that object in a container full of water. You'll notice that it feels lighter, or it doesn't feel heavy compared to when you hold that object in the air. It feels heavier when it's outside the fluid, and the object felt light when it's placed inside the fluid. So why does a body submerged partially or fully in a fluid appears to lose its weight? Or in other words, why does it appears to be lighter? And that's where the concept of buoyancy enters. Buoyancy is the tendency of an object to float in a fluid. All liquids and gases in the presence of gravity exert an upward force, known as the buoyant force, on any object immersed in them. Buoyancy results from the differences in pressure acting on opposite sides of an object immersed in a static fluid. As we know, the pressure in a fluid column increases with depth. Thus, the pressure at the bottom of an object submerged into fluid is greater than that at the top, which also means that the force exerted at the bottom of the object due to pressure will be greater than the force exerted on the top. This net upward force exerted on objects submerged in any fluids is called the buoyant force. And this is something that Archimedes has noticed. He postulated that the amount of upward force that the submerged object felt is actually equal to the weight of fluid that object displaces. And this is the Archimedes principle. So here, we're actually going to show this using some principles about forces and using the hydrostatic equations. To do this, we're going to think about the forces acting on some object that's submerged underwater that we see here. First is the force pushing down this object. Let's call it F sub down. And the force that is pushing up on the bottom of this object, let's take it as F sub up or upward force. As we can notice, they're both pushing on some area A, and for this example, we have an object with cylindrical shape. As we all know, pressure increases with depth. So at some height h, there is an equivalent pressure. There's a pressure at the top of the object with height h1, and there's also a pressure at the bottom with height h2 from the water surface or liquid surface. So by the net buoyant force, we have upward force minus the downward force, for which we know from the unit pressure, P is equal to force per unit area. Then from that, force due to pressure is equal to pressure times the area. Therefore, we have pressure at the bottom times the area of the object minus pressure at the top times the area. We all know that the pressure is equal to rho gh, where rho is the density of the fluid, g is the acceleration due to gravity, and h is the height from the liquid surface. Substituting this into the equation, we have rho gh2 times area, since the height from the water surface to the bottom of the object is h2, then minus rho gh1 times the area. Then we factor out the common terms such as the density of the fluid, the g, and the area. What is not common will be placed in the parentheses. We have h2 minus h1. As you can see in the figure, h2 minus h1 is just equal to h, which is the height of the object. And area times height is actually the volume of this object. By simplifying further, rho g is just the unit weight. So we have now the formula for the buoyant force. Buoyant force is equal to the unit weight of the fluid to which the object floats times the volume of the object displaced or submerged volume. Aside from the formula of buoyant force, we also have another formulas like the total volume, volume displaced, and the draft. Another formula for buoyant force is true weight minus the apparent weight, where the true weight is the weight of an object in the air and apparent weight is the weight of an object when submerged in a liquid. Then total volume of an object is just the volume exposed above the water surface plus the volume displaced, where the volume displaced is equal to the specific gravity of body over the specific gravity of liquid times its total volume. Or we could also have its formula in terms of unit weight. And lastly, the draft. Draft is just the height of the displaced body. And this is the formula for the draft. Now that we know the important formulas, let's try some examples. We have first situation here. A stone weighs 400 Newton in air and 300 Newton in a liquid having specific gravity of 0.86. Determine the buoyant force in Newton, the volume of the stone in cubic meter, and the specific gravity of the stone. Given in the problem the true weight or the weight of the stone in air denoted as TW, which is 400 Newton. The apparent weight or the weight when submerged in the liquid, that's 300 Newton. And the specific gravity of liquid, which is 0.86. Now we are tasked to find the buoyant force acting on the stone, the volume of the stone in cubic meter, and the specific gravity of the stone. From what we have discussed earlier, buoyant force is equal to true weight minus its apparent weight. So 400 minus 300, we have the buoyant force 100 Newton. Next is the volume of the stone in cubic meter. By summation of vertical forces is equal to 0, we have buoyant force is equal to the weight. Now, we already have the value of buoyant force from what we have obtained earlier, and weight is equal to unit weight of the liquid times volume displaced, or it is just the volume of the stone, where the unit weight of the liquid is equal to the unit weight of water times the specific gravity of the liquid. By substituting the given values into the equation, volume of the stone is equal to 100 Newton over 9810 Newton per cubic meter times 0.86. So the volume of the stone is equal to 0.01185 cubic meter. Lastly, let's solve the specific gravity of the stone. From the formula of unit weight, weight is equal to unit weight times volume. And unit weight of stone is equal to unit weight of water times the specific gravity of the stone. By substituting the values into the equation, we have 400 Newton over 9810 Newton per cubic meter times the volume. Therefore, we have the specific gravity of the stone of 3.44. We have our second and the last example for buoyancy. The problem states that the weight of a certain crown in air is 14 Newton and its weight in water is 12.7 Newton. Assuming that the crown is an alloy of gold with specific gravity of 19.3 and silver with specific gravity of 10.5. Assume unit weight of water 9.81 kN per cubic meter. Determine the buoyant force in Newton, the volume displaced of the crown in cubic meter, and the specific gravity of the crown. Given the problem, the true weight, which is 14 Newton, and the apparent weight, which is 12.7 Newton. The specific gravity of gold is 19.3 and the specific gravity of silver 10.5. And the unit weight of water is 9.81 kN per cubic meter. It is required to find the buoyant force, the volume displaced or the volume of the crown in cubic meter, and the specific gravity of the crown. So buoyant force is equal to true weight minus its apparent weight. 14 Newton minus 12.7 Newton, we have 1.3 Newton. Next, the volume displaced in cubic meter, or it is just the volume of the crown. By the formula of buoyant force is equal to unit weight of the liquid times volume displaced. Substituting all the values, we have the volume displaced, or the volume of the crown, is equal to 0.0001325 cubic meter. And lastly, the specific gravity of the crown. First, let's solve the unit weight of the crown. So weight over volume. 14 Newton over 0.0001325 cubic meter, we have a unit weight of 105,646.15 Newton per cubic meter, or 105.646 kilonewton per cubic meter. So getting the specific gravity of the crown is equal to unit weight of the crown over the unit weight of water. And we have 10.77 specific gravity of the crown. And these are the final answers for these examples. And that's it for this video. I hope you guys have learned something, and thank you for watching.